Welcome to the poster for Formulog, Datalog for SMT-Based static analysis. I'm Aaron Bembenek. This is joint work with Michael Greenberg and Steve Chong. Formulog is a domain-specific language for writing SMT-based static analyses that combines Datalog, a first-order fragment of ML, and SMT solving. And it makes it possible to write your analyses in a way that's close to their formal mathematical specifications and amenable to high-level optimizations like automatic parallelization. In this poster, we're going to build a reachability analysis where we take as input a graph where the edges are labeled with SMT propositions, and from this we determine which nodes in the graph are reachable given the propositions leading from the entry point to that node. Here all the nodes are reachable except for the node 4.
The first thing we need to do is define what a proposition graph looks like in Formulog. And we do that by defining a relation edge that says that there is an edge from one node to another node labeled with some SMT proposition, which in Formulog is a term of type bool SMT. And here in these 5 lines, I've gone ahead and enumerated all the edges in our example graph. You can see that this third column here consist of terms that represent SMT formulas. And it's worth noting that in Formulog, SMT formulas are data. They are just terms, like the number 1 is a term or the number 2 is a term. There's nothing really special about them. They can be inspected and manipulated just like any other term. Okay, so now that we have our graph representation, we can define the actual reachability analysis, and we'll do that by defining a relation reach, which says that some node is reachable following a path from the entry point with some path condition, which is the accumulated constraints along that path. And we can define the base case for our reachability analysis that just says that the entry point 1 is reachable with a path consisting of itself and with the path condition true. We now need to state a rule defining recursive reachability, and we'll do that here. First, we'll define a helper function mem, just checking for list membership, and then we'll define our recursive rule here. We'll say if there's an edge from x to y with some edge proposition, if x is reachable and y is not a member of the path leading to x, then construct a new path condition, which is the conjunction of the edge proposition and the old path condition, and check whether it's satisfiable. If all these conditions are met, then y is reachable along the updated path and with the new path condition. And on the back end, this satisfiability check actually calls out to an external SMT solver. So now that we've defined this rule, we can run the program. And you will see here that it finds that nodes 1, 2, 3, and 5 are reachable, but not node 4. So this is what we'd expect. Say furthermore that we really only care whether node 3 is reachable. We can add a query like I did on this line, and this will tell the Formulog runtime to rewrite our analysis to only explore parts of the graph that are relevant for answering this query. So when we run our program now, we will see that it says that nodes 1, 2, and 3 are reachable, but it doesn't explore node 5, since node 5 is not relevant for determining whether node 3 is reachable.
It's pretty neat that the Formulog runtime is able to do this optimization for us automatically. And while the example we've covered in the demo is simple, it's really not all that far away from something like symbolic evaluation or different types of model checking. Tune into our talk to see an extended example, learn about the advantages of Formulog's design, and see some interesting and promising performance results. Thanks.